Hello. In this lecture, I will discuss on hard soft acid-base theory. This is a part of your BTech chemistry syllabus in module 1. So I am Dr. Abhijit Shah. I am taking BTech chemistry course. So introductions about on hard soft acid-base. So hard and soft acid-base HSAB theory is a qualitative concept introduced by Pearson to explain the stability of metal complexes and the mechanism of their reaction. However, it is possible to quantify this concept based on FMO analysis using interaction between HOMO and LIM. According to this theory, Lewis acid and base can be further divided into hard or soft or borderline type. Arrhenius acid from hydronium ion in water, base from hydroxide ion. This definition assumes water as a solvent. Bronsted and Lowry expanded upon the Arrhenius definition and defined acid as a proton donor and base as a proton acceptor. They also introduced the concept of conjugate acid, conjugate base. And finally, there is one concept of Lewis acid, Lewis base. In Lewis definition, but a base is a molecule which can donate electron. An acid is a molecule which can accept electron pair. For example, if we have A and B, then if B molecule donating electron to A, so we will get A. The definition includes standard Bronsted-Lowry acid-base reaction. H plus aqueous plus ammonia aqueous will give ammonium plus Ag plus 2 ammonia will give Ag ammonia whole to aqueous. So this is the example of Lewis acid-base reaction. So when Lewis acid-base reaction occurs, it will form that Lewis acid-base adduct BCH3 whole 3 plus ammonia. If we perform reaction between these two molecules, then boron it has a vacant p orbital, and ammonia it has a lone pair of electron. So ammonia donates the electron to the boron p orbital, and it will form that adduct. The HOMO of Lewis base means ammonia interacting with the electron pair in the LUMO of the Lewis acid. Here BCH3 whole is the Lewis acid. A Lewis base has an electron pair in its highest occupied molecular orbital HOMO and suitable symmetry to interact with the LUMO of Lewis acid. In that way, this Lewis acid-base adduct is forming. Hard soft acid-base concept. Now, polarizability of an acid-base plays a role in its reactivity. Hard acid and bases are small, compact, and relatively non-polarizable donor atom, such as nitrogen, oxygen, fluorine. Soft acid and bases are larger, with more diffuse distribution of electrons, relatively polarizable donor atoms, such as phosphorus, sulfur, and chlorine. Hard-soft theory is an useful tool to predict thermodynamic stability or kinetic ability of metal ligand complex. But other important factors like Chillet effect, ligand field stabilization energy must be also considered and must be also considered to explain the hard-soft acid-base theory. Hard acids preferentially bind with hard base and soft acids preferentially bind with soft bases. This is the hard-soft acid-base principle. There is some examples of hard acid and soft acid and the characteristics of hard acid and soft acid. So if it is a small ionic radius for hard acid characteristics, small ionic radius, high positive charge, strongly solvated, empty orbital in valence shell, and high energy LUMO is the characteristics of hard acid. Example H plus lithium plus, sodium plus, potassium plus, beryllium 2 plus, magnesium 2 plus, calcium 2 plus. These are the examples of hard acid. Soft acid means larger ionic radius, low positive charge, completely filled atomic orbital, and low energy LUMO. Example: copper plus, silver plus, gold plus, mercury 2 plus, cesium plus, thallium plus, like that. Hard based and soft based. Hard base means small ionic radius, highly electronegative atom, quickly polarizable, strongly solvated, high energy LUMO. These are the characteristics of hard bases. Water, OH minus, F minus, Cl minus, CH3, COO minus, PO4 3 minus, SO4 2 minus. Okay, so they are the examples of hard bases. Soft bases, larger ionic radius, intermediate electronegativity, highly polarizable, low energy LUMO are the characteristics of soft bases. Example: RSH, RS minus, R2S, I minus, CN minus, SCN minus are the examples of soft bases. So there is some borderline Lewis acid and bases have intermediate properties. For example, in acid, iron 2 plus, nickel 2 plus, copper 2 plus, zinc 2 plus, right? In bases, Cl minus, Br minus, NO2 minus, SO3 2 minus, they are in a borderline. They are neither hard nor soft. Hard soft acid base principle or concept. Hard acid, the principle is hard acid prefer binding to hard bases to give ionic complexes. Soft acid prefer to bind with soft bases and give covalent complex. Okay, so if there is hard combination, it will give ionic complex. If there is soft combination, it will give covalent complex. Larger electronegativity difference between hard acid and hard base give rise to strong ionic interaction. The electronegativity of soft acid and soft bases are almost same and hence have less ionic interaction. That is, interaction between them are more covalent. If there is hard acid and hard base, there will be very strong ionic interaction. If there is soft acid and soft base, there will be covalent interaction. The interaction between hard and soft base, hard acid soft base or soft acid hard base are mostly polar covalent and tends to become more reactive or less stable. If there is hard soft combination, then the complex will be less stable. Polar covalent compounds readily form either more ionic or more covalent compound if they are allowed to react. Now application of hard soft acid base principle. First one, recovery of gold. So gold is a soft metal, is recovered by suspending it in a dilute solution of CN. So gold reacting with CN and we are getting UCN complex. Now gold is a soft metal, cyanide is also soft. So because of that we are getting this stable complex. Next is why silver iodide water insoluble but lithium iodide water soluble. Look, if we see silver iodide in water, it is there will be no reaction. Silver iodide in water, there will be no reaction. It will be insoluble. Why? Because silver actually soft. I minor iodide is also soft. So soft combination. So it will be stable combination. So in water, that combination will not break and it will not be soluble. But lithium iodide, here combination is hard. Lithium plus is hard and I minus is soft. So combination is a hard soft combination. So in water it will break and we can in water it will break and therefore it will be soluble. Solubility of lithium halide, it will be lithium iodide greater than lithium bromide, lithium chloride and lithium fluoride. Lithium fluoride will be very less soluble because lithium fluoride there is a lithium plus hard and F minus is a hard. So lithium fluoride is a hard combination, very stable. Therefore lithium fluoride will be very less soluble and lithium iodide will be more soluble. Okay, so these are the two applications. There are many more applications. Next one, in hydrogen bonding, the strong hydrogen bond is possible in case of water, ammonia, and HF. Since the donor atom, fluorine, oxygen, nitrogen, hard bases, the interaction particularly positively charged hydrogen, which is a hard acid. So in hydrogen bonding, the donor atom is fluorine, nitrogen, and oxygen, right? Because they are actually hard base, and hydrogen H plus is an hard acid. Because of that, we are getting strong hydrogen bond. Next one, precipitation reaction. Precipitation reaction, the soft acid like silver plus, H plus, Hg2 plus, and borderline acid like iron 2 plus, nickel 2 plus, copper 2 plus can be precipitated as sulfide from their aqueous solution because sulfide is a softer base, right? So sulfide is minus isn't soft. So if we use sulfide, so it can able to precipitate the soft and borderline acids. Other reactions. Other reaction means if we have a reaction between lithium iodide and cesium fluoride, then we you can see lithium iodide, lithium hard, I minus soft, cesium soft, fluoride hard. So this combination is not a stable combination. So if we react, it will give lithium fluoride and cesium iodide. So lithium fluoride is a hard combination, cesium iodide is soft combination. Now this hard and soft combination is a very stable combination. Because of that, reaction proceed in this forward direction. Silver at Agi2 minus is stable, but AgF2 minus is unstable. Right? Ag silver I minus is also silver soft, I minus is also soft. So both is in soft combination, and because of that it is stable. Now silver and fluoride complex, it will be unstable because silver soft, fluoride is hard. So hard soft combination, it will be unstable. Next one, cobalt COF6 3 minus is stable, but COI3 3 minus is unstable. Same, we can explain it similar way that COF6 3 minus here cobalt plus 3 oxidation state, which is hard acid, and fluorine F minus is a hard base. So it will be a hard combination. Because of that, it will be stable. But COI6 3 minus cobalt is an again hard, I minus will be soft. So it will be hard soft combination. Because of that, it will be unstable. So by hard soft acid base principle, we can explain which one will be stable, which one will be unstable. So there are hard soft acid base principle also applied to analyze, means to explain the precipitate formed in the qualitative analysis, right? For example, silver chloride precipitate is forming, mercury sulfide precipitate is forming, manganese sulfide precipitate is forming, calcium carbonate precipitate is forming. Now if we see carbonate it will be hard, calcium it will be hard, means calcium hard acid, carbonate hard base. So calcium carbonate hard combination, so stable and precipitated. If we check manganese sulfide, manganese 2 plus, it will be the borderline, and sulfide isn't soft, right? Therefore, if we use manganese sulfide, if you use H2S, manganese sulfide precipitated. Mercury is a soft metal. If we use H2S, that is then mercury sulfide is formed. Mercury soft, sulfide soft. So it will be soft combination. It will be stable. Silver chloride, silver soft, chloride soft combination stable. So like that, we can explain the precipitate from quantitative reaction and qualitative analysis by the hard soft acid base principle. Then ambidentate ligand. Ambidentate ligand like thiocyanate, isothiocyanate, they have two donor sites. One is nitrogen, another is sulfur. So nitrogen donor site is a hard donor site, and sulfur donor site is a soft donor site. So whenever we have metal like cobalt 3 plus, iron 3 plus, then nitrogen tends to coordinate because they are actually hard metal. If the metal is platinum 2 plus, mercury 2 plus, copper 2 plus, then they are the soft metal, then sulfur tends to coordinate. So in ambidentate ligand, which ligand will coordinate the metal ion, we can explain by Hartree acid-base principle. Similarly, cyanide, carbon atom on cyanide, Cn, then soft base. Okay, carbon will be soft, N will be hard. Okay, cyanide is in strong ligand in spectrochemical series. Okay, so this is all about Hartree acid-base principle. I hope you have understood. Thank you for listening.